inverse relations. So we have these two tables here, okay, and table A relates how many tickets were bought to how much they cost, and table B relates the amount of money spent with how many tickets were bought. Now, in fact, the relation shown in table A is the inverse relation of the relation shown in table B. Okay, so the inverse relations exist if and only if one relation contains the ordered pair BA, whenever the other relation contains the ordered pair AB. So you can see these values have been interchanged, and you can see that in the table here. So if you look at this ordered pair 1, 2, we also have this ordered pair 2, 1, or we have this ordered pair 10, 6. We have in the other relation the ordered pair 6, 10. So these two tables are inverse relations of one another. Now, in equation form, the inverse relation can be found by interchanging the independent and dependent variables. So let's consider the following here. So we have this equation y equals x squared minus 4. And then we have these table of values that correspond to this equation. So they satisfy this equation. Now, what do we mean by independent and dependent variables? Well, we can see from the equation the values of y depend on what the values of x are. So the y values are the dependent variable, which makes the x values the independent variable. Now let's look at the inverse relation of what we have here. Okay, so remember, to find the inverse relation, we interchange the independent and dependent variables. So we've interchanged the x and the y values. So this is y equals x squared minus 4. Then we have x equals y squared minus 4. And this is further supported by the ordered pairs from these table of values. So if we look at, for example, negative 3, 5 becomes 5, negative 3. 1, negative 3 becomes negative 3, 1. So we've interchanged the values. Now, if you look at the graph of this original relation here, we get the following. Okay, and the inverse relation looks like this. Now, you should notice that these two graphs are, in fact, reflections of one another in the line y equals x. And in fact, this relationship is true for the graphs of all relations and their inverse relations. Now, from the previous slide, we saw that these two graphs are inverse relations of each other. So what we'll do now is we'll look at them in terms of whether they are a function or not. Okay, now if you look at this graph of the original relation in blue, and we use the vertical line test, at any point where I draw this vertical line, you can see that it will only intersect once with the graph. This makes this original relation here a function. However, if we look at the inverse relation in green, you can see that the vertical line intersects the green graph twice. So this green graph is not a function. So although the original graph in blue is a function, its inverse relation is not a function. So its inverse function doesn't exist. In fact, not all functions have an inverse function. However, if the inverse relation of a function f is also a function, then it's called the inverse function. So if this graph in green was also a function, then it would be the inverse function of this graph in blue. We denote the inverse function of f as f inverse. Now we have to be careful, as students often make the mistake of confusing this negative 1 as an exponent. Okay, it's not, so just be careful. Whenever we see this, we are dealing with inverse functions. A function is said to be one-to-one if each value of y in the range corresponds to exactly one value of x in the domain. So if you look at this function g of x, this is not a one-to-one function. Okay, you can see this value of 5 within the range of g corresponds to 2 values within the domain of g. Now f of x here is a one-to-one function because each of these values corresponds to exactly one value within the domain of f. A function f has an inverse function f inverse if and only if it is one-to-one. So looking at this diagram, the function f of x, what it essentially does is takes values from within the domain of f, so this set of values, and maps it to corresponding values of f of x. So this becomes the range of f. Now what the inverse function is, it reverses the process. So we start off with these range of values of f of x, we input this into the inverse function, and then this maps it back to the corresponding values in the domain of f. Now since we input these values into the inverse function, this becomes the domain of f inverse. And since this is our values of outcome, this becomes our range for f inverse. Okay, so it's important to see that the domain of f is the range of f inverse, and the range of f is the domain of f inverse. Now let's look at the key concept of the horizontal line test. So a function f has an inverse function f inverse if and only if each horizontal line intersects the graph of the function in at most one point. So looking at this example here, if we draw in a horizontal line, we can see that since no horizontal line intersects the graph of f more than once, the inverse function f inverse exists. So in our example here, this function f of x, or this graph, this passes the horizontal line test. Example 1. Graph each function and apply the horizontal line test to determine whether its inverse function exists. Part A. The function f is equal to the absolute value of x minus 1. So we'll draw the graph first. And now when we draw in a horizontal line, we can see straight away it fails as test, as it intersects at more than one point. So we can conclude that f inverse doesn't exist. Part B, we have the function g of x. So when we draw its graph and try to draw a horizontal line, you'll find it's not possible to find a horizontal line that intersects the graph of g more than once. So it does pass the horizontal line test, and g inverse does exist. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. Example 2. Determine whether the function f of x has an inverse function. If it does, find the inverse function and state any restrictions on its domain. Step 1. We'll draw in the graph of f of x, which looks like this. Then we'll apply the horizontal line test, and you can see this passes. So therefore, f is a one-to-one function and has an inverse function. Now, looking at the domain and the range, let's look at the x values first. So you can see it begins at x equals 4, and it increases unbounded towards positive infinity. So we can write this interval down for the domain. And for the range, it starts off at y equals 0 here, and again that increases unbounded towards positive infinity. So we write this interval for the range. Now for step 2, we want to find the inverse function of f. So we begin by writing the original function down. And then what we'll do is we'll replace the f of x with y to give us the following. And then we will interchange x and y, okay, to give us the following. And then we want to solve for y. So we'll begin by squaring each side, and that'll give us the following. Okay, and then when we solve for y, we get y equals x squared plus 4. So we'll then replace y with the inverse function notation. So we can have over here the inverse function of f of x is equal to x squared plus 4. Now for step 3, we want to draw the graph of y equals x squared plus 4. So this is the graph we get, and we want the domain for this. So we look at the x values, and we can see it's unbounded going towards negative and positive infinity. So we can write this interval down for the domain. For the range, we look at the y values, and you can see it begins at y equals 4. Then it increases unbounded towards positive infinity. So we can write this interval down for the range. Now, when we compare the domain over here with the range of the function f, you can see they're not equal. And if you look at the range over here and compare it to the domain of f, they are equal. So what we want to do with this domain here is we want to restrict it so that it has the same interval as the range of the function f. Okay, and then we can say that the domain and the range of the function f is equal to the range and the domain of the inverse function respectively, and then we can write this down finally. Now it's your turn to have a go at answering these questions. so pause the video before I reveal the answers. And the answers are the following. An inverse function, f inverse, has the effect of undoing the action of a function f. For this reason, inverse functions can also be defined in terms of their composition with each other. Now let's look at the key concept for compositions of inverse functions. So, two functions f and g are inverse functions if and only if f of g is equal to x for every x in the domain of g, and g of f is equal to x for every x in the domain of f. Example 3. Determine whether the function f and the function g are inverse functions. Now, to verify this, we want to show that f of g equals x and g of f equals x. So let's begin with f of g. Now, g of x over here can be replaced with what we have over here because they're equal. Okay? And then, because we're dealing with the function f, the x value for the function f, we replace this with what we have over here within the brackets. That gives us the following. Now we can expand this bracket using the distributive property to give us the following, and when we simplify this, we get the value x. Now looking at g of f of x, this function f of x, okay, we can replace this f of x with what we have over here because they're equal to each other. And then we're dealing with the function g. Now what we do is the x values in the function g, we replace this with what we have here in the brackets, and that gives us the following. And when we expand this bracket using the distributive property, we get the following, and then when we simplify this, we get the value x. So we've shown that f of g is equal to x and g of f is equal to x. So therefore, f and g are inverse functions of each other. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. Example 4. Use the graph of f of x, which is this graph here, to graph f inverse. So the first thing to do is to draw the line y equals x. Okay, then we locate a few points on the graph like so. And then what we want to do is to reflect these points over here in the line y equals x. So let's begin with this one. Okay, when we reflect this, it'll be located here. And we do the same for these other points. Okay, and now what we want to do is to connect these points with a smooth curve that mirrors the curvature of f of x in the line y equals x. So we draw a smooth curve connecting these points, mirroring the curvature of this graph f of x. Okay, and now we have the inverse function for f of x. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following.